Hi class. Uh, this video will talk about projectile motion, and I will show you how we can use the two equations of kinematics we have to model how projectile motion works, or at least describe it. Um, First of all, I'd like to explain to you what projectile motion is. So projectile motion is any motion of any object in which the only acceleration that is being experienced is the acceleration of gravity. So, if you had, anyone sort of throwing any object, and you might know from sports that, if you have any ball and you throw it like this, you might know already that um, the path here is a parabola, right? Now, this qualifies as projectile motion because the object here is the only acceleration that it's undergoing when it is on the air is the acceleration of gravity. So let me also give you a different example, one that will be a little more useful. So imagine you are inside a cabin or something. There's something like, it could be a train or it could be an airplane, could be anything like this. And there's a person here. They're holding a ball. And they throw the ball up and down. So they keep throwing this ball up and down. And if you're watching this person, and if the box here, let's say it's a train car or something. So it's some sort of train car on some rails. If the box is not moving and there's, let's say there's a window, then you can see that the ball is just going up and down, right? Ball is just going up and down. And that makes sense. Now stop for a minute and think about what would you see if now this cart was moving. So let's say now the train is moving along and moving across this velocity v of the train, right? Now you're just outside, you're an outside observer, so you're right here and you are observing this happen. If you could trace out the path of the ball, do you have any guesses in how the ball would be perceived to move if you're on the side of the road here, looking at this train car? Okay, you might or might not have some guess, but let's say that at some time t later, the box is right here, and the ball returned right here. What happens here is that the ball, when this person threw the ball started going up, right? Up, 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 up. But the train was also moving to the right. So when the ball reached its highest point, it was right here, and then it starts falling again. And sure enough, this would look like a parabola. And you can sort of think of it this way. If you're on a level road, let's just assume you're in a level road and a passenger in your car is just taking something in their hands and throwing up and down. Just because the car is moving does not mean that the ball is going to move relative to the person's hand. It means that person, hand, the car, person, ball system all moves in unison. But a person on the side of the road won't see that. If they're looking at the ball is going to go up and down inside whatever is moving, but the whole structure is moving. This is a very nice example because it says one thing about projectile motion. It says that so I'm going to erase this observer here. The ball's y motion is independent of the car's x motion. In this statement, I basically already assign a coordinate system in which this is a plus y direction and this is the plus x direction. What do I mean that the ball's y motion is independent of the car's x motion? It means that the ball undergone its y motion going up and down inside the car, and the only reason you observed a parabola is because you also observed the car's x motion. And so the projectile motion for this object in the red line is the addition of the y motion of the ball and the x motion of the car. Hence, you can treat them independently, which means that you can have the equations for the x. So this implies equations that describes the x motion that are different than the equations of the y motion. Okay? So that is what projectile motion, and this is the argument for why we can do what we are about to do, which is expressing the equations of motion in the x and the y. So let me clean that example problem a little bit. First of all, the first thing I'm going to do is I'm going to assign a y direction. So up is plus y, which means anything that points up is plus, and it goes in the y equation. And I'm going to call the x plus x, meaning anything that points to the right, it's going to be positive, and it's going to enter the x equation. And now any projectile motion that has an x and a y component, and it is not being acted by any force, or actually is not undergoing any acceleration other than gravity, the path will be a parabola. And we can describe this path very well. So the first thing I'm going to do is I'm going to bring up the two equations, the master two equations of kinematics. Basically, if you want to describe motion, the only thing you truly need is two equations. So it's velocity final, acceleration times time, plus velocity initial. And this gives you the relationship in between velocity and acceleration. And then the next equation is the displacement final equals to 1/2 the acceleration times time squared plus the initial velocity times time plus the initial displacement. Okay, these two equations of motion is everything you need if the only thing you need to do is describe the motion. You don't have to model why motion happens. And these are really good at describing the motions of point particles that don't interact with anything. They're just, the only interaction is the acceleration term here. Okay, great. Now, what's going to happen is we're going to break this down into x and y. As I said before, projectile motion is a combination of x and y motion, and those motions happen independently, meaning that the x motion can have their own kinematics equations, and the y motion can have their own kinematics equations. They will no longer be vector equations because we will be treating each dimension independently. So let's first of all work out the equations in the y. Now, y is a little special. Oh, actually, let's do x first. X is simpler. And why is x simpler? So let's look at acceleration. If nothing is acting on the object except gravity, gravity only acts down. And so the acceleration in the x here is 0. So when we go ahead and write the equation for the velocity in the x, what happens is the acceleration is 0 in the x. So the only thing you're going to have for x is the velocity final in x is equal to the velocity initial in x. And note how I'm still using the term velocity rather than speed with the arrows, and because this can be positive or negative, right? So the x direction is still a direction with a positive and a negative. So these are still vectors. This is still velocity. Right, and so for the displacement in x, instead of talking about displacement, I'm just going to assign the coordinate x, just for clarity. So here, x final is equal to, so acceleration is 0 on the x, so this whole thing goes away. The only thing that's left is the velocity initial in x times t, which also happens to be the velocity final in x, meaning that the velocity in x is constant. And then the only thing left is if you had some x initial, if you chose the 0, 0 not to be at the start, you would have some x initial. And sometimes that's useful to do. So let's treat the y direction. Now the y direction has the acceleration here. The acceleration in the y equals to minus g, meaning is it's minus g. And so meaning that the acceleration in the y direction always points down, and it's always 10 meters per second squared. So the velocity final in the x, velocity final in the y equals to minus g times t plus the velocity initial in the y. And we have done an example like this in class when we were talking about the acceleration due to gravity. So if you look back in your notes, you should have something like this already done. Okay. What we have not done yet is this, the y displacement. So y final equals to, now we have an acceleration, it's minus 1/2 gt squared plus the velocity initial in the y times the time plus y initial. Meaning that if your initial position had some coordinate, then you could insert that in there. Most of the time, whenever the axes touch, this is going to be your 0, 0 point. If that's the case, then the x initial and y initial will go away. And we will see that in a couple of examples. So one quick thing I want to point out is how the velocity vectors sort of work. I'm going to use the greens here for the x. Do you see how the velocity final of x is equal to velocity final of y? Meaning that whatever velocity in the x direction just carries over throughout the whole motion. So velocity is not changing. But when you look at velocity for the y, you have this minus, this gravitation acting on it. Meaning if your initial was positive, you give enough time, this other side is going to be 0, and that moment will happen there. So here you have some initial velocity there. Over here you would have a 0, and as we talked about last time with gravity, you end up having a reversal here, over here. And what happens in between? Well, this arrow keeps getting smaller and smaller and smaller until it flips around, and then it gets bigger and bigger and bigger until you get the full motion. Okay. All right, so with these 4 equations, you can solve any projectile motion problem that you are going to be asked in this class. So this is a special case of the 2 kinematics equations we saw last video, but these are useful when a projectile motion. So these are useful when an object is undergoing projectile motion. Projectile motion happens when an object is moving, and the only acceleration it is experiencing is the acceleration to gravity. A final note, the one thing that I see every year with confusions as far as the subject is choosing appropriate final and initial points. So you have initial and finals for everything, initials and finals, initial and finals. And the best thing I can describe how that works is that you're going to first thing you're going to decide on a coordinate system. Usually it's always going to be x and y in this case for projectile motion. And whenever they intercept, that's going to be your 0, 0, meaning x and y is 0 over here. Just like in math class, this is just a regular Cartesian coordinate. In the projectile motion happens all of this, right? So let's pick a point. We're going to pick this point right here. And at each point, you're going to have a number of things. You're going to have an x, you're going to have a y, you're going to have a velocity in the x, velocity in the y, and you're going to have the time. The time is the time since the motion crossed the 0, 0 point. So this is defined as the 0 time point. So each point in this arc is going to have a different x, y, vx, vy, and t. Now, you can call any point initial and any point final. So you could potentially call this point final and then go ahead and call this point initial. And so the x, y, vx, vy, and t initial becomes actually time is always counted from the initial, so I'm going to get rid of it from this list just to focus on the positions and velocities. We don't deal with changing times in this class. In this class, your textbook does not do change in time. So the time is always measured by where in the 0 here. So final, when I mean x final, y final, velocity final, y, basically is whatever point in the trajectory you pick to call your final. Whatever x, y, vx, vy is there is what enters these equations. Same thing with the initial. And with that, I will show you a couple useful points. So most of the problems, most of the problems in this class will give you information about where time equals 0, meaning that the motion starts here. So this would be a very good initial point to consider when you're doing your problems. And then final basically means pick a final in which solves for something you're interested in, right? So if a problem asks you, what's the maximum height that this arc happens? The maximum height will be the y coordinate at this point. So it would be useful to treat this x, y, and all of these quantities as a final quantity. And so when you solve for y over there, you know where the highest point is. Another thing is called range. Range means when this thing hits the ground again, what is this distance right here? And so range means that it's the x coordinate at this point. In that case, setting this point to final would be really useful, right? Because x final will then be the range you're looking for, all right? And the last thing I want to talk about is that there's a couple of properties that come in really useful as almost like shortcuts to solve these problems. And it is, I think we talked about a couple of these already. So if you pick the highest point, velocity y at this point is 0 meters per second. And we sort of talked about this, right? So if you have a positive initial velocity popping this object up against gravity, gravity's work against it until at some point it will momentarily stop moving in the y coordinate, right? Then the other useful thing to know is that if you're comparing the same heights, so this height and this height, whatever velocity at this height on this side of the trajectory is, you take the length of the arrow or how much the velocity is and you just flip directions. And this doesn't work, this works with final and initial of the total trajectory, but it works at any point. So I could, let's say I had velocity information here, and for some reason it's useful to have velocity information here. All you have to do is to flip the velocity. So this trick of knowing that the velocity at max height equals 0 and that the velocity flips on the y's when you cut it, the trajectory height-wise, are two shortcuts I will show you how to use when tackling problems on your homework. Okay, well, thanks for listening. I hope homework is going great. Reach out if you have any questions or if you would like any help. Have a very good day, and I'll speak to you all of you soon.